So right triangle trig. What do you guys remember about right triangles? Guys, what do you guys remember about right triangles? Well, you have a right angle. What's they have four sides. Very good. What is always opposite the right angle? Hypotenuse.
Oh, that's a word I haven't heard in a while.
Now, what happens here is the legs of a right triangle, it doesn't really matter which one's which. They're just a leg. What's more important is when you place an angle. Did you guys use theta last year?
Yes.
Okay. I'm going to use angle theta. Yeah, I used x left. I'm going to start using theta, okay? Now, theta stands for an angle, okay? Now, remember, angles always look at their sides opposite, which makes the side next to it, it's adjacent, which therefore reminds you of Chief Sokotoa and the proud Indian tribe. Do you remember Chief Sokotoa?
Yeah.
What's that?
Mr. Sam never did Chief Sokotoa.
No?
I remember.
He did do theta though.
Well, I mean, he taught us Sokotoa.
You didn't hear the story? Okay. So Chief Sokotoa, the Indian tribe of the Hypotenuse back in, forgot which one, they had to develop a way to come up with how to measure out distances for their arrows. So, you know, how far out things were going to shoot, because they can walk a distance, they weren't sure how far out, and what launch angles and stuff like that. They were very crazy about that. So what they did is they came up with the whole idea of, oh, it's opposite hypotenuse. So they named it after the chief. That's where someone told it.
That's a weird story.
It's a true story. You can do that.
I thought it was just made up.
No. The Indians were trying to protect themselves. They happened to know math because they were friends with the Greeks. They traded with the Greeks. You know, fair trade, the whole thing. They had salt. The Greeks wanted salt.
Did you get a haircut?
I got them all cut.
A what?
Got a hair's cut.
Did you get one?
Do you get your hairs cut?
Yes.
Wow. Are you sure you got every single one cut?
Pretty sure there aren't any stragglers. I hope. So you have your three trig functions. This is what you did last year. What changes up this year then is that we introduce you guys to what are called inverse trig functions. Now, inverse trig functions are literally, when you inverse a fraction, what do? You flip it. So when we talk about inverse trig functions, they are going to be what's called cosecant, secant, and cotangent.
Did you do that last
You might have. Okay, you might have. I think Sev might. I know I didn't.
That sounds familiar.
But sine and cosecant are inverses of one another. Cosine and secant are inverses of one another. Tangent and cotangent are inverses of one another. Which means if sine is opposite of hypotenuse, cosecant would be, yep, you just flip it.
I don't remember spelling it that way.
What's that?
I think you had to do like the
There's other ways of doing it. I'll show you what we're going to do with it here today. Because eventually what we're going to do is, when we get to the non-calculator stuff, we get to start doing stuff where we graph, where a sine graph looks like this. Inverses are, you invert particular points. If you think of it in a fraction, what's the inverse of 0? It would be 1 over 0, which means it's an asymptote. Because can you divide by 0? So you would get an asymptote. So I just do this. I have an asymptote here. What's the inverse of 1? The inverse of negative 1. Negative 1. The inverse of a half. The inverse of a half. So what happens is that you get inverse relationships, and we look at more of those as we get into graphing of the functions. We do it that way. We look at it in terms of solving equations when we bounce them in through the unit circle. That's when we spend more time with inverse functions. Today, it's just a matter of, can you write them out in terms of right triangle trig stuff? Okay? It's nothing too crazy. All right? Just a matter of getting the names down. So, excuse me. So we have all these, nothing fancy, which allows us to do, well, let's go to the next part, the specials. 2 special right triangles. What's one of them?
45.
You have your 45, 45, 90, and your 30, 60, 90. Now, your 45, 45, 90 was created from the diagonal from a square, if you remember that. Now, do you remember what their side lengths ratios were? What was it, Trav?
Wasn't it Q, and then like Q root 2?
Right. I don't use the Q's like Seb does. I just use X's. And eventually I'm just going to turn them into 1s. Good. Which one was where?
X was between 60 and 90. So across from 30.
Yeah, across from the 30, yep.
Across from the 60.
Whoa, whoa.
But across from
Yeah.
them. But it's not X.
Oh,
Because what happened was is that the 30, 60, 90 came from an equilateral triangle. If you think back to your equilateral triangles, if they're equilateral, that means all the angles are the same and all the sides are the same. So if these are all 60s, if you draw the perpendicular bisector to the side, that's where you get your 90, which means that these two parts are cut in half. So if the whole thing was this, that's where you get your opposite, your 30, is the 1, 2, 1 squared plus something squared is 2 squared. That's where you get the root 3. That's where all that comes from. Okay, that's where that came from. Now, what we're going to do is, for today, I'm usually set it up as that x, 2x, the x root 3s and things like that, because those of you guys that had me, because you guys were awesome, I use that, what I set up as, remember the algebra trig? Which side do you know across from, what can you set it up for, and solve for the missing part. We do the same idea here as you go through it. Now, these 2 triangles are the most important thing you're going to ever remember from geometry, because that's what's going to allow you to do this, because it's going to allow you to find all these critical values as you go forward. As we go forward, the only angle measures that are going to matter to us at all, probably towards the latter half of next week, is those 30, 45, 60, and 90. Those 4 angles. That's the only 4 that really make any difference to us whatsoever. In about 2 weeks. For now, we're just trying to review it. Okay. So what I want to do is walk through the specials. I want to walk through the special angles via their trig functions. Because the quicker we're able to figure out trig functions of our specials, the easier everything becomes. There's a reason why I like to do this. So if we have if I write it as 1, 1 root 2, is that okay for 45s?
yes.
Now, no matter what, if the side lengths are 4, it would be 4, 4, and 4 root 2. So as it simplifies itself out, no matter what, it will always be that ratio. It will always simplify out to being 1. Same deal with the 30, 60, 90. If I do my 30, 60, 90, then I do that. Now, what I want you guys to think of is that when you are the angle You are the theta. What are you looking at? So if you go through and look at it as being the sine of 30. Well, if you're at 30, what are you looking at? What is your opposite? It's 1. So what's the sine of 30? 1 over 2. It's 1/2. Oh, I'm pretty sure I don't think any of you guys do this in here. I don't remember yelling at anybody. No slashy fractions, please. Slashy fractions are bad fractions. We want regular fractions. There's a big reason later on. Slashy fraction? Bad. Icky bad. Oops. Cosine. What's the cosine of 30?
Root 3 over
Root 3 over 2. Good. What would the tangent be? What's the tangent of 30? Well, what's opposite your 30? It will be when you rationalize. Very good. It's going to be 1 over root 3. But we always rationalize that. Remember, we don't like radicals in the denominator? So you multiply top and bottom by root 3, and you get root 3 over 3. Cosecant. Cosecant is the inverse of what? Trig function. Sine. So what's the inverse of 1/2? 2. What's the inverse of root 3 over 2? You flip the fraction, and you get
2 over 3 over 2.
2 over root 3, which you get, when you rationalize it, you get, good. You guys all remember how to rationalize, right? I'm hoping. And then what's the inverse then of 1 over root 3? Our original tangent would be root 3. Okay. Not so bad.
Wait, how did you get the first, like, how did you know that the sine of, like, theta 30 is?
What's opposite to 30? 1. What's the hypotenuse? 2. Remember, the ratio of the sides will never change. If the opposite of 30 was 6, that means the hypotenuse had been 12. So 6 over 12 always simplifies to be 1/2. That was the whole idea of working with the special array triangles, so that way these ratios always occur. And that's what we use a lot. A whole lot. Same deal with the 60. Now, when you're at your 60-degree angle, now what's your opposite? Root 3. So your 60 has an opposite of root 3 over, so your sine will be root 3 over 2. Its cosine would be 1/2. The tangent then is, excuse me. What's that? Root 3, good. And now it's a matter of going through and doing all the inverses. Once you go through your inverses then, if you flip, bless you, if you flip the root 3 and 2, which we've done before, you wind up with 2 over root 3, which meant it was 2 root 3 root 3. You'll also come to realize that a lot of these things are duplicated. They're just shifted over. Hint, hint. What's the inverse of 1/2? 2 thumbs up. See what I did there? No, that doesn't there. And last but not least, the inverse of root 3. Good. Root 3 over 3. Okay. And then you go to the 45s. 45s always are going to have the root 2's thrown into them. So if you're at a 45, your sine and, remember, your sine and cosines for 45s are always the same. Because your opposite, if you're placing your theta here, your opposite is 1, your adjacent is 1. So that means your sine and cosine values are always identical, no matter which one you're at. Because if you're up here, you're still a 45, and your opposite is 1, and your adjacent is 1. So if your sine is 1 over root 2, we write it as root 2 over 2. Excellent. And what's your tangent? 1. Okay. Now, think about flipping things. When you have a 45-degree angle, your opposite is your 1, your hypotenuse is root 2. We just automatically wrote it as root 2 over 2 because we rationalized it because that's what you know, that's what you learned before that you want to always do. Excuse me. So now, if your sine and cosine are root 2 over 2, what's going to be your cosecant and your secant? Just root 2. Because if you think about it, your opposite is 1 over root 2, so your cosecant then would be root 2 over 1. Your secant would be root 2 over 1, so they're both root 2. And what's the inverse of 1? Just a little FYI, I do know that Miss Denny regularly uses this as a quick quiz, a times test, if you will. I think they get a minute. And if you know your specials, it's very quick to do. Okay? If you know your specials, it's very quick to do. I don't know, I haven't decided. I've never done it as a times test. I do some things with pop quizzes and trig a lot, but I don't normally do it out of this one. Okay. We good on these? All right. Oh no, I don't know what to do. I am afraid. Yes, sir. I can't hear you. 5 root 3? How did you get that so remarkably quick? Magic. Quick reminder, obviously this is a right triangle. Everybody okay with that? Because the little red square kind of helps out a little bit. This is a 30, 60, 90. This is that setup that I usually did, that I taught my geometry students. I used it I always use this one with the honors class, and I actually, when I taught pre-calc last year, I still brought this same setup back into play because it's one of those things that it shows you that, hey, my 30 is looking at a value of x. My 60 is looking at that value of x times the square root of 3. My 90 is looking at 2 times something. So which of these side lengths do you know? You know across from the 90. Well, that has to equal 10. The reason why I set it up this way, because it takes a lot of the thought process out of play, because you're left with a one-step equation. 2 times 1 is 10. So once you get this value of x being 5, everywhere I see an x, I replace it with a 5. So like Trap said, that's got to be 5 root 3. Granted, hopefully as you knock the cobwebs out of your brain from last year, you'll be able to look at that and say, oh, it's going to be 5 root 3, and you can go on from that way. But if you forget, this little algebra trick is a nice little thing to use. Now what? Remember what it meant to solve a right triangle? Find everything, yeah. Find everything. So what happens here is that, do you also remember that when you have angles, angles are always capital letters, lowercase letters are the sides opposite them? You guys remember that? I would hope. Please. So if you're looking at this and you have 20 and a 12, what are the other things you have to find? Well, I have to find angle B. I don't think Seb used the angle with an arc in it, did he? The reason why I do it is because that's what my geometry teacher did back in, and it just stuck with me. Plus, a lot of times that looks like a less than symbol, or sometimes it looks kind of like an L or an upside down 7. So I don't know. Plus, when I marked up diagrams before in geometry, you would like put in a tick mark for like showing things were congruent. That's just how I was taught. So if you see that angle with the little slashes, that's what that means. Just using an angle measure. So you have to find angle B, little b, and little c. Whew. Whoa. SMRT. Remember the little trick in geometry that if you have a right angle, the other two angles have to be complementary. So they have to equal 90. So that's where you get that. So yes, you get 70. One thing I will recommend, if you can get away with not reusing something that you solve for, do so. Because let's say you were an idiot and you forgot that they add up to 90, you actually thought they added up to 100 and you wrote down that it equaled 80. If you reuse that angle that you were wrong with to begin with and start doing trig with that angle, will your other side lengths ever be correct? So what I always try to do, and I want to try and instill in you guys, is to try to reuse all of your given statements as much as possible. In this example, I was given the 20 degree, and my 20 degrees looking at its side opposite, which makes C the what? The hypotenuse, and B as your adjacent. So if you know an angle, you know an opposite, what trig function are you going to use to find the hypotenuse? Sine. Good. So you have the sine of 20 is 12 over C. This is where, see if you remember this. Is this a true statement? What am I going to write this? Is that true or false? 2/4 equals 3/6. It's true. Is this a true or false statement?
No. Wait, false?
True or false?
True.
True. Is this true or false? True. What am I doing? Moving. Very good. What did I move? Numbers. I'm moving things on the diagonals. Does that change anything? Anytime that you're trying to solve for the variable that's in the denominator, no matter what, when you're dealing with trig stuff, all we do is this. Exchange-o, change-o. Exchange with the diagonal. It's the quick way to remember. Exchange-o, change-o. It's dumb, it's stupid, but it works. Because you're going to see that a lot. You're snickering, but it's true. Because when we get into law sines, law cosines, things like that, when we're going to have variables on denominators, you're always going to sit in the back of your mind, oh, it's exchange-o, change-o. So it's just a matter of typing it in the calculator correctly. Your calculator should be in degree mode. Remember to hit the button that says mode and make sure it's highlighted underneath where it says degree. If it is not, please make sure you do so. Also, anytime that you, well, these guys don't have batteries, so you don't have to worry about that, but if you ever have a hard reset on there or you do anything like that, always go back and double check your degree mode. When we get to quizzes and tests, things like that, I will always remind you guys to go with degree mode because
It looks like it's highlighted in gradient.
and then just move it over to the right and then hit enter and then it'll redo it. Because if you get into radian mode, yeah, it's going to be all sorts of messed up because it's dealing with things in terms of pi. We're not there yet. Okay. So back into here, all you have to do is, this one isn't so bad because there's not a lot of real math going on. If you just type in 12 divided by the sine of 20 and hit enter, you're going to be okay. All right. Once again, I generally say always round to 2 decimal places. I don't think that changes really anywhere in the book. It usually says, I think the book says 10th, but always go 2 for me because that's better. So if it is 35.085, what am I going to write that as?
35.09.
Very good. So 3509. Now, even though I know that my hypotenuse is now 3509, what happens if I screwed that up and I use it again to figure out the adjacent? Will I ever get my adjacent correct? No. That's why I want you guys to continually reuse that given and use a secondary trig function to find that missing side length, the next one. So if you have a 20, you have an opposite, and you have to find the adjacent, what trig function works with opposites and adjacents? Tangent. So you do the same idea. Tangent of 20 times 12 over b. Once again, exchange-o, change-o. And type it in. One thing I will ask of you guys to do, because I know that this can go rather quickly. If we're not careful about what you're typing in, you're gonna get everything wrong. So please, 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 please. See where I'm at right here, when I wrote, for side C, I wrote 12 over sine of 20. For side B, I wrote 12 over tangent of 20. Write down what you're going to put in the calculator before you put it in the calculator. Because there are so many times that I see students that do that, and they accidentally type in 11 tangent of 20. Or they'll type in 12 divided by tangent of 10, or they'll hit 12 divided by sine of 20, just by pressing the wrong trig button. But they wrote down the right answer. They just had a bad thumb moment. I'm able to figure that out. I can tell what you did wrong pretty quickly if you happen to do something like that, but you have to show me what you're doing before you do it. Does that make sense? I know that a lot of this stuff is really easy and you can fly right through it, but if you're not careful, you can make a dumb mistake. And that's why I always ask you guys to write out your answers before you put it in the calculator. It helps you, because I won't yell at you then. It's very common.
So you give us like credit for it?
I usually do, yeah. I usually do. I think there was an example of that on the test from the other day. Somebody wrote out everything they were going to put in the calculator, but when they put it in the calculator, they flipped a couple of digits. And I was able to figure that out. I'm like, how did they get the answer? They wrote that up. I messed with what they wrote down just by, on my calculator, trying to figure out, like, working it backwards, see how they did it, and they flipped numbers. I'm like, oh, you know what you're doing. You just typed it in backwards. You're using two thumbs, and your left thumb got ahead of your right thumb. That's all. It happens. It's totally understandable. But if you tell me what you're doing, it's great. My geometry class this year, I actually gave them a quiz where I took away their calculators and said, hey, write down what the answer is without putting the calculator. Put it in the calculator. That way you know that you know what you're doing. Works out a lot. That's all. We all remember this, I hope? Ish. Do I need to do another example? I don't know if we'll get to this today. Oh, do you remember how to find an angle?
Use data.
The inverse button, yeah. Okay.
What?
The inverse button.
The inverse button and then you put data equals something.
Here, let me show you real quick, just for.
Why, do we have to do that on our homework?
Probably. I remember if this is on this one. Looks like no button.
Yeah. I know, right?
Actually, I studied actually. My grade is at 89.45.
For something like this, if I want to solve my right triangle knowing this, if I want to solve knowing my right triangle doing this, so if I go this route, well, what's the easiest way to figure out little b? Pythagorean theorem, that's a great idea. I'd use Pythagorean theorem, that's a great idea. What's the Pythagorean theorem?
A squared plus B squared equals C squared.
Okay, so 10 squared plus something squared is c squared. So b squared is 44. Do you remember how to simplify, to do simplified radical form? Remember how to check it? Now this calculator doesn't do simplified radical form right off the bat. It's going to give you a decimal. So if I take the square root of 44, what's the perfect square that's hiding in the 44? 4. So it becomes 2 root 11. Do you want to check that in the calculator? Did I show you guys how to do that before? Let me show you. Since in this unit, what I want you to do is go to your calculator where it says to your y equals table. Oops. And anytime you ever want to find out a simplified radical form, what I would do is this. I type in 44 divided by x squared. Because what it's doing, it's going to generate values of x. It's going to choose values of x and see which perfect square, what number squared, goes into 44 the right amount of times. So you check your table.
Oh.
Now, if I go back to my table and I'm looking at it, what it's saying to me is this. Let me blow this up so you can see it better. It says 44 divided by 1 squared is 44. 44 divided by 2 squared is 11. 44 divided by 3 squared is decimals. And once I get to the point where it's all decimals, that means it's not going to happen anything after that. Which means that it would be 2 root 10. You guys ever see that trick?
Wait, you mean 2 root 11?
Did I say 10? Yes, 11. Thank you. It would be 2, the answer would be 2 root 11. That's how this always works. That's how you can find, how you can simplify radicals with this calculator. Because unlike the multi-view, which was the greatest calculator ever, up until being able to graph, you can do it this way.
Why didn't you show us this earlier?
Thank you.
I swear I did.
Yeah, you did.
I swear I did. Because then I remember saying that, oh, this works for cubes. Also, you just divide by
Yeah.
x cubed or x to the fourth. It always works. Because we don't use it all the time. Okay? But you'll use this in here because I'll say it's simplified radical form. Or decimals for angles and things like that. Anyway, back to this real quick. So if I know that I have my two side lengths, this is 2 root 11, I'm not going to reuse this one because I just found that. I'm going to pick out an angle. I'm going to pick B. I'll choose B to find first, which means 10 is what in relationship to B? Adjacent. There's my adjacent, here's my hypotenuse. So what trig function am I going to use to find B? Cosine. So here's what happens. We have the cosine of theta is 10 over 12. Do you ever have to simplify any of these fractions before you put them in the calculator? No. Nope, nope, nope. How we do this in the calculator, though, is this. We do 10 over 12 and hit enter. You get some funky decimal, which means that the cosine of some angle equals that funky decimal. Here's what you do. Second cosine of your answer. Use the answer button as much as possible. It will make your lives so much easier because you're not trying to round things off. You're not going to get any rounding error or anything like that. Use the answer button and hit enter.
Wait, when you put after cosine?
Answer.
No, like in between.
I just hit second cosine of my answer.
Oh.
I typed in my fraction first, and then I got that funky decimal, and then I went from there. So that tells me my angle B is at 33.56. And then what trig function do I use to find A?
Second answer.
I use sine for that one.
Second.
And I always double type everything in, just in case I typed in something wrong with my cosine. And that's how I get my two angles. You guys remember how to find inverses, right? To find the angle. What angle has the decimal? Good.
Can't you just do 180 minus the...
What happens if you did it wrong? Will that x angle be wrong?
Yeah, but wouldn't it also be wrong if you used the wrong B angle? Like,
What I'm saying here is that if you did this, and we got, what was our, I forget what we got. Was it 30, what was it for this one? 33.56?
Yeah.
Okay. So let's just say you typed it in, you got 33.56, but then you start subtracting stuff out. What happens if you went from 100 minus 33? People do that all the time because they forget that it's 90. For some reason, people always think these two add up to 100. I don't know why. It just happens. You'll automatically be wrong. Or if you wrote this thing down wrong, or you hit the wrong trig function to get to this one. But by reusing what you were given and changing angles, you're just switching trig functions. You're just using two trig functions to get to your answer. That's all I'm saying. What's that?
Think you add up to 90, that's a good way.
Yeah, it's a good way to check it then. Yeah, sure.
I didn't get 33.56. I don't know if I'm putting it in. Because I put cosine into that.
You get,
Oh, wait. Yeah.
let's see. use the answer button. That's why.
Isn't it the same?
Why waste your time? You make it harder. 10 divided by 12, hit enter.
Wait, did you use?
Inverse cosine of your answer. What degree mode are you? What mode are you in?
I had it on what's that?
There's your problem. Yes, sir.
Sorry.
You just put the cosine negative one and then make a fraction.
If you want, that's fine. There's the reason why I did the extra steps because it gets funkier later. That's all.
Wait, when you found the last angle, did you use 33.56 or did you just do the?
I just did another trig function.
Okay.
That's all. Because what happens if you wrote that down wrong? Then you'll be wrong no matter what. Okay, that's all. I'm trying to get you guys to remember just to reuse givens. We'll get into angles of elevation, depression, all that kind of stuff tomorrow. That's all fun. Let me give you some problems to start. There's a couple other little trick things we'll do tomorrow as well, as far as trig units. Let's see, let's do this. So this is 13.1. We'll just do those for now. Because then we'll get the angular elevation stuff tomorrow, and then I'll do the other funky stuff with the inverse trig functions as well. Because what I want you guys to be able to do is this, eventually, is find the sine of theta if tangent of theta is that. That's a very important thing to be able to figure out for when we get to this. Ote? Go from there.
What's your website again? It's www.
I don't know. Have you checked an email at all recently from me? Because it's in my footer for my emails.
No, I know. I have it like bookmarked in my Chromebook, and my Chromebook is dead, and every time I try to look it up on my phone, I can never find it. It's like
Oh.
Murphy Math something, right?
Yeah, give me a sec. I'll pull it up here.
Like, what's the exact web address?